Buonasera, ladies and gentlemen in the audience, and also people from the internet. First of all, I want to thank the organizers for giving me the opportunity to speak here. And I also want to thank the organizers for being that persistent and after 2 years doing this conference, this workshop. So I think that's really very, very cool, and I'm glad to be here. Unfortunately, we don't have the full lineup here, but it's still a very, very nice experience. So thank you very much for that. I also want to thank Simone and all my previous speakers for setting the stage. So I don't have to talk about many of these things and can talk about a few other things that I want to show you. So in particular, I want to focus on the sodalite-like clathrate hydrides that have been mentioned in the talk of Yangming Ma already, and the talk by Defang Duan, and then also by Simone. So as you have heard, they are structures with a large gas atom inside a hydrogen cage. And these are highly symmetric structures. And these are hydrides that feature the highest TCs that have been found up till now, more or less, and can even go up to room temperature. So I mean, this is can you see my, yes, you can see the pointer. So you can see this figure here that Yangming Ma already showed an updated version, but many of these hydrides that you see here are actually the clathrate structures. And you heard a lot about different numbers, pressures, and TC values, but I want to use this opportunity to dive into a bit more detail about the superconducting state and the properties of these materials. So first of all, the binary ones, yttrium H6, yttrium H10, for example. So if you look at the electronic structure, on the top figures are the Fermi surfaces dressed with respect to the hydrogen content. And here you can, and the bottom figures are the electronic band structures along the high symmetry lines. And something that has already been mentioned before, what's interesting here is that what's important is that you have a lot of hydrogen, that you have a lot of hydrogen states at the Fermi level. This is also what you can see here. So greenish, yellowish, reddish colors would be a lot of hydrogen, bluish colors would be very little hydrogen. And you see here in this Fermi surface very, very nicely that in the Fermi surface center bands, they are yttrium-like, whereas the states at the Briançon edge, they are more like hydrogen states. And the same applies for the yttrium H10, where you have a very tiny surface, Fermi surface in the center, and then you have this large, big blob around the edges, which are basically mostly hydrogen. And this is important for us because, as was already mentioned, we want the hydrogen states to couple to the hydrogen vibrations. And this works perfectly nicely in these yttrium compounds, for example. So here I'm showing you some calculations done with the fully anisotropic Migdal-Lierschberg theory that Roxana will introduce or explain on Thursday. So also don't need to do that now. I just want to say that we get the Coulomb, the screen Coulomb interaction from GW calculations, and then use the Maurer-Anderson pseudopotential formula to get to this mu star. So in a sense, I mean, one could argue, is this fully ab initio? It's not, but that's what we do. And you can very nicely see the superconducting gap function here developing with temperature above here, and you get the TC where the superconducting gap function vanishes. And what you also see very nicely is that you have two peaks, or two features here. You have a small feature over here, you have a larger feature over here. And if you then plot the superconducting gap function on top of the Fermi surface again, you very nicely see again that this large feature here corresponds to this mainly hydrogen lattice, hydrogen states, whereas the lower one is occurring at the Fermi surface center. So these are the states that are more strongly hybridized between the yttrium and the hydrogen. And just because sorry, there's one slide missing, and I don't know why. Now, yeah, because it was mentioned today. So this is actually something that I didn't want to show you, but I put it in today because we were talking about why we need hydrogen bands at the Fermi level, and this would be the example of iron hydrides that have been measured in experiment, and at least the structure was measured, and was proposed that they could be very good superconductors, actually high TC superconductors. And what you see here is if you look at the Fermi at the electronic states here, dressed again with iron DEG and iron T2G, that the Fermi surface is basically made out of entirely from these iron D bands, whereas you have almost no hydrogen content at the Fermi level. And if you do the Michel-Lierspect calculations there, you get a TC of 0 Kelvin. So this is why we want to have hydrogen at the Fermi level. Right. So as the Fermi surface has so much hydrogen, and the hydrogen is, or the coupling to the hydrogen is the largest actually, you can also do, you save some computation effort by doing the isotropic Michel-Lierspect theory, which gives very good results for these cleft structures as well. What we also find is that in these yttrium compounds, we get a very weak dependence of TC on pressure, which is what you see here along this line. So particularly for this yttrium H6, which is stable for quite a wide pressure range, you get quite a stable TC. And this is partially due to compensating effects of increasing electron phonon coupling in the lambda and decreasing omega log. So these are the two counter active effects here. And we ask ourselves the question, of course, can we do better? Can we do better than these yttrium compounds? And the answer was given already by Simone in his previous talk. So he stole my thunder a bit there. And I thank Chris Pickett for this expression. I didn't know that. Yeah, what Simone did basically is he searched so basically motivated also by this experiment where you have lanthanum, hydrogen, and then some element. He was trying to find which element can we put in, what is reasonable, and which structures do you get. And he found that if he looks at these, or if he does the calculations, then he gets this lanthanum boron H8 structure that was mentioned several times already. And the interesting thing here is you have again the hydrogen cages that surround the large gas atom, the lanthanum, and then the boron fills the smaller void. So you have a very, very efficient packing of your unit cell. And this then leads, as has been mentioned before, to an enhanced mechanical and chemical pre-compression, and boron exerts this additional pressure. And I want to summarize these findings by Simone again by saying that they are thermodynamically stable, or this compound is thermodynamically stable above 100 gigapascals, but and is metastable below. And as already been mentioned by Chris Pickett, it might not be the best idea if you're searching for a very good superconductor to look at the ground state structure, because the metastable structures might actually be the ones that are more interesting in terms of what's going on at the Fermi surface and so on. So if we look at the Fermi surface of this compound and the electronic properties, you get the following picture. Again, you see we are not at the, we don't have a peak actually at the Fermi level in the DOS. So we rather have a, yeah, not a pseudo gap, but it's actually going down. But we do have a lot of hydrogen, and what you also see, we do have a bit of lanthanum, but we have very, very little boron if you look very closely at that. And on the right, again, the Fermi surface, very similar picture to the yttrium compound before. You have hybridized states between the lanthanum and the hydrogen in the Fermi surface center, in the Briançon center, sorry, and then the Briançon edges, you have basically very pure hydrogen states. And this again justifies the picture that the boron in this compound acts as an almost inert spacer and helps us put more pressure on this compound. And if you calculate the phonons and the electron phonon coupling for this compound, you realize that the electron phonon coupling is actually spread over quite a range of the phonon dispersion. So it's not like that you have one or two phonon modes that carry almost all of your coupling, but it's if you see here, I mean, a lot of phonon modes are taking part, and this is because you have the Fermi, the electronic structure at the Fermi level is so much hydrogen, and you couple to all these hydrogen vibrations then. But what you also see if you look at this as a function of pressure, that in particular these modes here, as you go down in pressure, the modes at the gamma point, they start to develop an instability from becoming anharmonic, and we estimate this to appear between 35 and 40 gigapascals of pressure. And then if you do superconducting calculations for quite a couple of pressure ranges, you actually see that Tc now increases with decreasing pressure. So as you approach the instability, you increase your electron phonon coupling, and this gives rise to a larger Tc. And again, on the right, the superconducting gap function on top of the Fermi surface is very, very isotropic in this compound as well. So we again ask ourselves the question, can we do even better? And what we started from is this lanthanum boron H8, which again is dynamically stable at about 35 gigapascals if you just look at the phonons, and has a Tc of about 126 at 50 gigapascals. And this is already a quite good start, we thought. I mean, the pressure is 5 times lower than in the lanthanum H10, for example. But still way too high for any actual technical applications. So what basically Simon again did in his structural searches was to look at 54 different combinations of elements. So you take this 118 structural template, and you replace the X and the Y with different elements, or basically the neighboring elements, the rows and the columns of your periodic table, close to the boron and to the lanthanum. And then we investigated the phonon stability for these structures at 50 gigapascals. And as it turns out, there are only 2 more compounds that are stable, dynamically stable with this template. And this is barium silicon H8 and strontium silicon H8. And again, I want to mention here that further ternary crystal structure prediction calculations were performed for these 2 systems. So a full convex hulls for different pressures for these materials. And what we find is that these structures, they are thermodynamic. Basically, so the 118 stoichiometry is present at more or less all pressures that we looked at. But this one particular, the FCC structure that we want to have, this very, very nice clathrate structure, is only stable, thermodynamically stable above 100 gigapascals. And below that, or 150, sorry, and below that, it is metastable. But again, metastable structures might be more interesting to look at actually than the ground state structures. So again, the electronic properties of these compounds. You see that, again, a different picture now if you look at the dose. So you are now right at the shoulder here for this barium silicon H8 at 5 gigapascals. And what you also see, so that the filled space is hydrogen. And you see that basically at the Fermi level, you have no barium contributions, you have no silicon contributions. It's basically hydrogen. And a very similar picture we get also for the strontium. Here we are a bit further along this shoulder. We are now actually at this plateau. And again, most of the states that you see here are coming from the hydrogen. So this gave us really a lot of confidence and hope for the superconductivity calculations that ensued. So first, before I present you the TC calculations, I want to show you again the phonons and dynamic stability. So again, we calculated the phonon properties for these two compounds. And we did this for quite a range of pressures. So from 0 gigapascals to, I think, 50, 70, 80 gigapascals. And what you see is, I mean, you have a few modes, of course, that as you decrease pressure, that start to become soft. And in order to be as accurate as possible and still being able to do our Migdal-Eliashberg calculations, we then started to correct these harmonic frequencies by anharmonic calculations. And in our work, we chose we used the frozen phonon approach. So what you do is we set ourselves, so we chose a 2-2-2 supercell, and in this supercell basically corrected every soft mode that we found by fully mapping the potential energy surface with respect to the displacements of the phonon, of the particular phonon modes, and then solve the Schrödinger equation for these eigenmodes. Right. And what you see here is, so in the solid lines are the anharmonic calculations, and in the dashed line are the harmonic calculations. And I also want to mention here that we tested for phonon-phonon interaction by coupling 2 or 3 modes in this approach as well. So you don't have to look at just one phonon eigenmode, but you can do the same thing for 2 eigenmodes simultaneously by looking at in a 2D surface, or you can actually then couple 3 modes by looking at 3 displacements. It's just that the calculations then become more and more expensive, as you can imagine, because you need a lot more structures. Right. So long story short, if we do our anharmonic calculations, the dynamically critical pressure for this barium compound drops to 3 gigapascals compared to the 5 gigapascals of the harmonic approximation. So you don't gain a lot, you gain a tiny bit. And for the strontium, we find that we have a critical pressure of about 25 gigapascals. But, and I want to mention this right now before you get wrong ideas, we don't think that these pressures are actually the pressures at which you can fully stabilize these compounds. So we actually think they're becoming unstable before that, and we are arguing this with the kinetic stability that I will talk about in a few seconds. But before I do that, I first want to show you our TC calculations, the results for our TC calculations. You see again the 2 gap functions here for the barium in this compound at the bottom here. So you have this very nice drop at about 71 Kelvin. And for the strontium, we have a higher TC, but also a higher pressure of 30 gigapascals. And we're now at about 126 Kelvin, more or less the same as the lanthanum boron H8, but 10 gigapascal or 20 gigapascals lower in pressure. What you also see is that these 2 gaps now for the Fermi surface, the center band and the bryones on edges, they have now more or less completely split. So you have basically a very nice two-gap feature of your superconducting state there. Right. And if you then monitor the dependence of Tc with pressure, you get, again, a very similar picture as with the other clathrates, so that Tc is rather constant through this whole pressure range that we looked at. So for the barium here, for the strontium here, and again, partially to these two competing or cancelling effects of lambda and omega log. And with that, I now want to address the elephant in the room, or the question I raised before. Namely, we don't think that in looking at phonon instabilities, phonon dynamics is not the proper way to estimate the stability for these compounds, because we think that looking at the enthalpy barrier is actually a much more realistic and better way of estimating this, and should give more realistic effects. And what I mean with that is, so as I mentioned before, these compounds are only thermodynamically stable above 150 gigapascals. Below that, they're metastable. So there is a ground state that is better in enthalpy. And you find the ground state on the right hand of these plots here. So these points would be the ground state. And the first points here that you see, they are the actual structure that we're interested in, so our clathrate structure. And we're using this variable cell nudged elastic band. We're basically searching for the best path to connect these two structures, right? And we then calculate the enthalpy for every single intermediate structure that we find and plot it as I've shown you here. And what you see, for example, at 100 gigapascals, you see there's a very, very nice and large enthalpy barrier protecting this structure, from decomposing, no, come on, sorry, to go into the ground state structure. But as you decrease the pressure, you see that this barrier drops significantly. And as you go below 35 gigapascals, so in that case, so 10, you have only a very tiny barrier left, which won't protect the structure anymore from thermal effects or from impurities and all that stuff. And if you plot this, just the height of the barrier as a function of pressure, you get the following plot, where you see that for very low pressures, there is basically only 10 millieV per atom, so not very much. But then at 30, it starts to increase considerably. And this is the point where we actually are quite confident that this might be the pressure where you could be able to synthesize and realize this structure and keep it stable. Again, this structure is quite a lot higher in pressure than the one from the dynamic stability, even if you include anharmonic effects on the frozen phonon level. And we also think that this reasoning applies to many other superconductors. It might be the reason why so many hydride superconductors, but also looking at other structures apart from the hydrides, have not yet been able, or experimentalists have not been able to calculate, or to synthesize these structures because they are just not stable at these pressures that they were predicted to be stable, because these were given as dynamical pressures and not looking at the kinetic and metastable stability of these. With that, I'm at the end of my talk, and I very quickly want to summarize what I showed you today. So I've been focusing on the ternary superhydrides, which enable a considerable reduction of pressure while still maintaining a very high TC. I've talked a bit about the lanthanum boron H8, which is very interesting. It has a TC of about 130 Kelvin and is dynamically stable down to 35 gigapascals of pressure. Then we have variations of this template, of this 118 template, which is the strontium siliconate and the barium siliconate, and in particular for this barium siliconate, we do have to take a bit of a hit in TC, so it's only 70 Kelvin only, but it's stable, dynamically stable down to 3 gigapascal of pressure. But we think the actual stability barrier that you should look at is the kinetic one, which is at 30 gigapascals of pressure. And I hope I could convince you that this, of our idea that this kinetic stability is a more rigorous estimate for judging the stability of a compound than looking at the dynamic one. And with that, I want to thank all the people involved in this work, which is Simone and my PhD student, Roman Lucrezi, which did the superconducting calculations and the anharmonic calculations there. Also, a lot of thanks go out to Lilia and also to Giovanni Bachelet and to our funding sources, which are the Austrian Science Fund and then yeah, the Italian sponsors of Lilia and Simone. And at this point, I also want to thank you for your attention. Thank you very much.